Good morning, everybody. Out of 60, we had 28 people right now in class. So please don't forget to send me the video. I want to take care of business before I continue. And one of the things that I want to point out is that yesterday we're talking about the limitations, and some people after the class were still asking me the same question. So don't forget that for Well on page 16.1, 119 and 120, we had a limitation. And the one that we're talking about yesterday about the minimum length of the well is given at the top of the page 16.1-120. And also, thank you, Christian. Also, I forgot to mention that in this class, we are not going to change the grading. We're going to use the same grading system that we always use. So it's going to be A, B, C, and unfortunately D, F. So it's not going to change. But in the classes, they're going to give you grade or no grade. You still can select to get a letter grade. But in this course, we are not going to change. Also, so we still have the A, B, C, D, whatever. Want to remind you this is important. Next week, the exam is on Tuesday. We're going to start at 7 o'clock in the morning. Just imagine right now, we have 35 people. Just imagine that you're late. So you have to start at 7 o'clock. I know that parking in your house is difficult or whatever. You need to be at 7 o'clock and you have 1 hour to upload your exam. It's better to get partial credit than not to get any credit at all. So you need to, the first problem by 8 o'clock, you have to upload it. The second problem you can download at 8 o'clock, but also in this screen, the second problem will appear for 1 hour. And also by 9 o'clock, you need to upload it. So you need to start practicing about scanning, but make sure that I can read your exam. And the same happened with the bonus. Uh, I already put this in Blackboard, the bonus you have from 9 until 10. So make sure that you understand that at 10 o'clock, no more exam will be accepted. So it's better to get partial credit than no credit at all. Any question before I start solving problems? Will we get in partial credit for the third question? You're going to be getting partial credit for the first question. You're going to be getting partial credit for the second question. You're going to be getting partial credit for the third question. So, and remember what I told you in the face-to-face lecture, that the only reason why some people go to the next level is because of the partial credit. So definitely you're going to be getting partial credit. But I was saying that it's better to get partial credit than no credit at all. So make sure that you upload your exam. These are the rules, very simple rule. So make sure that you follow the rule. Any other question? You remember, you have more questions at the end of the lecture, you can ask. You had good memory. This is the same problem that we solved yesterday. This is exactly the same shape, the W10 by 49. And these are exactly the four plates that we had yesterday. The only difference is that instead of being a welded connection, this is a bolted connection. The question here, it is a tension member, so you don't have to worry. Look in here, it says tension member. You don't have to worry about determining if it's eccentric shear. It is a tension. And the shape is given. And there are four plates, two in the web, two in the flange. and they want to find the design strength. And remember, phi T sub n is equal to T sub u. And also remember it is a 25 footer. So you have to check the K, the L over R. And it says here two lines of bolts in each flange. So when you look at the flanges, this is one line of bolt, this is the other line. So each line of bolt has three bolts. So here on the top flange, in the top line, look, there one and two lines, and each line has three bolts. So here on the top flange, how many bolts do we have? Anybody, right? How many bolts we have in the top flange? Six. And hey, turn the mic off, please. And so six. Please turn the mic off. Six on the top flange. The second question for everybody is this single or double shear? Single or double shear here? Single shear. Good. So we had on the top flange and the bottom flange, we have single shear. And on the web, we had this is one, two bolts, and we had two lines of bolts. So how many bolts do we have in the web? No. So make sure that, especially since it's gonna be an open book, open notes, and you can have solution minus and everything, make sure that you read this problem, because normally I don't like open books exam. I remember going to mechanical engineering to Proctor, an open book exam. The students spent 30 minutes looking for a similar problem they couldn't find. So make sure that you read the problem and answer the question. Now I'm gonna go and solve the problem. Hugo, just to answer the question, it's not required because you don't have the thickness, you don't know the material. So read the problem. Okay. So in this problem, and it was a bonus, the design strength. And remember that 3 to n larger equal tu. So the design strength is also tu. That's why I put it here, tu. The length of the member, 25 foot. The bolt 78A3225X, the material LA992 grade 50, 8 inches. And I put in here thickness to ask you the question already asked you. So from chapter 1, the gross area, the same gross area that we used yesterday, the thickness of the web, 0.34, the thickness of the flange, 0.56. For a wide flange, the thickness of the flange is always more than the thickness of the web. The reason is that we want to have a large concentration of area away from the neutral axis, because the moment inertia is the moment inertia about the own central axis plus the area distance squared. So we want to have a large moment inertia. That's why we had a large area. That's why the flange, the thickness for a wide flange is always more than the thickness of the web. And R2Y was 2.5, and the required was L times 2 over 300. For tension, we do not use the K. For compression, we use the K. So it's okay. So making a point in here that I only have information on the shape. So since this is tension, I had to do all the limit states, because in here, the problem here says consider all the limit states. So remember, for tension, we have tension yielding, tension rupture, we have bearing, we had a capacity of the bolt in single and or double shear, and we had block shear. So there are 5 limit states. And I started with the first one in here, yielding. So it's phi times Fy. This is the gross area. Look, the gross area is in here. So if yielding were to control 648 kips is the design strength of this connection. Rupture, we use the U factor 1 because we're using the entire cross section. We're using the flanges and we're using the web to transfer the load. So this is a very important step. When I go back to this and look, help me before. Look, whenever we had tension, this is the load. This section perpendicular to the direction of the load. Look at this section perpendicular to the direction of the load. We had the flanges and the web. So this cross section at this location is this one. So this is a cross section that we have. And that's why at the beginning of the lecture, I asked you, look, this is like any normal problem. This is the tensile load perpendicular to the load at this location. This is my cross section. So like you all said before, 1, 2, I have four bones. We don't see in both web and flange is that the inner one control. Edgar, look, physically at this location, this is the cross section. So at this location, we had four holes in the flange. And this is the thickness of the flange. Whenever we subtract from the total gross area, we're going to subtract 4 holes that they are in the flange. So this is the thickness of the flange. And the thickness of the flange is more than the thickness of the web. Whenever we go to the web, we're going to subtract 2 holes. And this is the thickness of the web. So we do not use the thinner or the thicker. We consider what physically is in there. So at this section, we have 4 holes. 4 holes in the flange, 2 in the web. So I'm going to go back to this. Thickness of the web and the thickness of the flange. So if you look in here, gross area 14.4 minus 4 holes in the flange. Diameter of the ball plus 1A, 0.56 is the thickness of the flange. Minus the 2 holes that are in the web. 2 times the diameter plus 1A, this 0.34 is the thickness of the web. So the net area was 1148. When I gave this exam, only, let's say, out of 65 students were able to consider. Whenever something happens in a class, I don't blame you, I blame me. So I understand that probably I didn't cover this correctly. So when I grade, I consider that it's not your fault, it's my fault. But in this case, I'm telling you in detail, if I give you something like this and you made a mistake, it is your fault. Any question about this? Look, 4 in the flange, 2 in the web. Any question, any clarification? And this is like in the class. Some of you understand faster than the others. So if you still don't understand, you don't want to ask right now, ask me later. I will turn my computer on and I show this to you in detail. But the point I want to make is whenever you look at this tension member and we look at this section, when we had 100% of the load, like we normally do, we had 4 holes in the flange and only 2 holes in the web. That's why the net area had 4 holes in the flange, 2 holes in the web, 11.48. So the limited state of rupture, phi times Fu, the reduction factor U is 1 times, so this is the net effective area, 559.65. Right now, this is controlling my design because it's smaller than this. So right now, what is controlling my design is rupture. The next limit state is the bolts. I'm going to go back to the top. And I ask you this question. I don't know what Edgar means for time consideration. Maybe I figure that out later on. No time consideration. If you're saying that you're gonna consider the thinner one, that's the time consideration. That is a mistake. That is a terrible mistake. So if you consider it here, all of them with 0.34, that is a terrible mistake. Nothing to do with the time. It had to do with understanding of the problem. And I think that's where you. Okay. So we're looking at the board right now. And I asked you this question before. You have to be looking at this cross section. And before I ask you, single shear and double shear. Whenever we find what is the design strength of the connection based on the bolts, how many bolts do we have in single shear? Anybody? How many bolts are in single shear? Not for the cross section, for the entire, because whenever we find in the design strength based on the number of the bolt, so look, there are two in here, two in here, two in here, so we have 6 and 6, 12. 12, that is correct. How many bolts do we have in double shear? 3 and 3. So make sure that you look at this because that's the correct answer. Single shear 12, double shear 6. That's what you told me, and that is the correct answer. Since this is exam number 2, I told you you can go to chapter 7, table 7-1. And I expect you to do that because time is very important. And I want to point out something. Look, this comes from the chapter 7, table 7-1 for single and double shear. What I want to point out is that in the all exams, in previous edition of the code, this value was different. This value has increased, those values have increased. So some of the all exams, and somebody asked me yesterday, and I forgot to mention to everybody, some of the all exams is not that it's wrong, it's that we had different values. Every time that they do research and they determine that there's more strength in what we believe or that they didn't have that much capacity, they revise. They create new numbers. So this comes from 7-1, and these are the new numbers for single double shear. So we had in single shear 12 times 30.7, in double shear 6 times 61. So the capacity of this connection based on the number of volts, I need to move this a little bit. The capacity of this connection based on number of volts is 736.20. So what is controlling my design right now? What is the design strength if I end the problem here? What is design strength? Rupture. And how many kips is that? 559. So now we need to do either block shear or bearing. And what I did the next step is bearing. So I'm going to go to the top again and ask you some questions. These dimensions are given. Let's look at the top. Can I do the bearing in the plate? Can I do bearing of this plate? I just want to find out if you're paying attention. Can I do bearing for this plate? No. No, because we don't know the type of material, we don't know the thickness, so we cannot do. So I have to do bearing only on this flange. So for this flange, this is my external ball, and these are my internal ball. So you look at this beam, or when you look at this beam in here, this is the end. This is the end of my girder. So this in here is this external, and these are the internal. And so I'm going to have to do the L to C exterior and interior, or the flanges. In the flanges, how many exterior, if we consider top and bottom flange, for the flange, how many exterior bolts do I have for bearing? Very good. Let me tell you, look, this is my cross section, right? If you go back and look in here, look at this cross section. And imagine that it is one, because all of them are the same. How many bolts do I have here on the top? And how many do I have in the bottom? So altogether, there are 4 still. What about the interior in the flange? How many do I have interior, top and bottom flange? Good. Okay. So let's look now at the web. This is the exterior, and this is the interior. In the web, how many exterior bolts do I have? 2. And how many interior? And the thickness of the flange, as you know, is different than the thickness of the web. So everything that you're telling me right now is given to you. So you do have to be careful. And look, during the exam, if you cannot understand any sketch, just ask me, and during the exam, you have to have the camera on, because really I miss you. I want to see your face, but the microphone has to be off. And so you go to the chat, and yes, I will clarify. If I can clarify, I will clarify. It's something that is, I'm not going to give you the answer, but I will. So feel free. Don't panic and drop everything and run across the neighborhood. Just relax and ask me, and I will clarify. So I'm going to go to the next page. I'm going to do the flange. And remember, 1 hour to solve this. Can you clarify number of bolts? Sure. Yeah, I know it's difficult. You do need to pay attention. I'm going to repeat this. All that I have is time. I know that you have to go to another class at 11, and you have to drive across the campus. So, but I had time and nothing to do. I'm bored here at home. So I'm going to tell you again, we're doing bearing. Whenever we do bearing, we have to consider the plate or the shape of both. Right? But in here, there's no information on the plate. So the only thing that we can do is look at the shape, at the type of 10 by 40. And this is the end. This is the end of my beam, because I'm using the plate to transfer the load to the other side. Whenever I look at the flange, this is my external wall, and these are internal wall. The same here at the bottom, exactly the same. This is my external, those are internal. So we need to know how many bolts I have at the outside and how many bolts I had inside. because in order to find the bearing strength, we're going to multiply the number of volts outside or stereo, and we're going to add the capacity of the interior. So this cross section applies to any location. This cross section is typical cross section. So whenever we look at this cross section, imagine this cross section is in here. And we look at how many bolts we have here at the top. We had 2 bolts. We had here at the bottom, we had also 2 bolts. So this stereo for the stereo for bearing, we had 2 plus 2, 4 bolts. Whenever we had what remains is all of this. At each section here, we had 2 at the top, 2 at the bottom, 2 at the top, 2 at the bottom. So if I tell you that stereo for the flanges only, we had 4 bolts. For the flanges only, how many bolts do we have altogether? Answer any. No. I'm saying, look, here, these are stereo bolts. Stereo bolt, we have 1, 2, 3, 4. Interior bolt. How many do I have at this section interior? You look at this section. How many do I have interior just for the flange? How many? How many at the top? How many at the bottom? So how many do I have here and how many here? 4. And how many here and how many here? So all together, how many do I have interior bolt? 8. Okay. So now we're going to look at the web only. The web is easier to look. These are stereo. How many stereo bolts do I have? And this is the web. This is the cross section for the web. How many do I have in here too? And how many do I have in here? 4. Okay, so that's the way we do it. I know that is difficult. Just look at this section. This section is the typical. So based on what I think that you all understand. And this is the geometry that cannot be changed. 1 and 1A, 1 and 1A, 2.5, this cannot change. It's like the previous exam that some you change what was already fixed, what we call typical. This is here my typical cross section. So what we have in here, flange and web. So I'm going to go to the flange. The flange, this is 1 and 1A minus, I have to subtract half a whole. And remember, I know the first exam was before the spring break and before all these problems that we have right now. So this is the only time that we use 1/16. This is basically a standard hole. As you remember, the standard hole is more than 1 inch. The standard hole, it is the diameter of the ball plus 1/16. If you were able to measure a standard hole with a caliper, with high tech, with low tech, it is 7/8 plus 1/16. So this is a length, 1 and 1/8 minus half a hole. This is the only time that we use 1/16. This is 0.66. For the interior, the distance center to center of the holes is 2.5. We have to subtract 1 hole. That's why we have 2.5 minus 1 hole, and the 1 hole, diameter of the ball plus 1/16. So now this, as you remember, is steering. And the second equation, it is the bearing deformation of the hole. In the previous code, we did not have divided into steering and deformation of the hole. Everything was together. Now what I'm doing in here, this is the steering. This is for the stereo, and this is for the interior. This formula is in the code in the bearing portion. Just, I don't want to offend anybody. But I just want you to refresh your memory because it's been a long time. Bearing the formation of the whole 2.4 DTFU. And in here, tear out 1.2 L to C TFU. So these are the equations that I'm using in here. 1.2.66. What is this 0.56? Times 65. I'm going to go back to the page. The thickness of the flange and the thickness of the web. I hope you're not getting dizzy with me doing this and going back. So, since I'm doing the flange, this is the thickness of the flange. This is the thickness of the flange. This thing here is FU. So 6827 for the stereo, 3644 for the, 2883 for the stereo, 6827 for the interior, and the formation of the hole, 2.4, the diameter of the ball, the thickness of the flange times 7640. We always compare the number. This had to be smaller than this number. This had to be smaller than this number. So in here, I'm finding partially based only on the flanges. The flanges, 4 stereo balls that you told me at 2883, 4 stereo holes, 2883 times 4. 8 interior at 6827 because it is smaller than. So right now, the flange alone, based on bearing, had a capacity of 496.11 K. Any question before I continue? You say we do not check for the tear because bearing is bigger. No. What I'm saying is that the code always require this in here. This equation 1.2, this is tearing. And this in here, the formation of the hole. We always, I think that you need to hear better, or maybe I need to be clearly what I'm saying, is that the code. And it's not me, it's the code. Look, bearing and tearing. Bearing, you have to check. Oh, it was a spring break. No, you're drinking too much or something. No, I did not say that. Look, always the deformation of the hole, 2.4 DTFU, is the maximum value. So you have to compare the tearing, this value, with that value. Nothing can be larger than this value. So we always had to do tearing, and we had to do the formation of the hole. It happens in here that for the stereo it's smaller, for the interior it's smaller. That's why we're using those values. But nothing can be larger than this value. So based on the flange, bearing on the flange, we have 496.11. Any other question? So now I need to do bearing in the web. And that's why in here I call the web. It happens that L to C exterior and L to C interior are the same for the flanges and the web. So this value 0.66 and 1.563, they are the same as before. The only thing that changes is value 0.34. What is this 0.34? What is this 0.34? Thickness of the web. So based on this computation, steering 17.50 for the exterior and for the interior 41.4. Deformation of the hole, look, 0.34, 46.41. So if we compare 17.5 with 46.41, this control. 41.45 with this still control. So in here, I did phi times 2 exterior plus 4 interior. 2 exterior, 4 interior in the. And this is what I done in here. 2 exterior, 4 interior, give me 150/60 only. And adding, look at this value in here. The value of the flanges and the value of the web, I had add them in here. So based on bearing 646.71, what is controlling my design so far? We had yielding, rupture, bolt and bearing, rupture still. So the last step is to do the block shear. And for the block shear, the web, look, like we did yesterday, this portion in here is connected to the web. So the only thing that's going to have is going to be also a double L. And this distance in here has to be determined. This distance has to be. What is the flange? What is in here? The width of the flange. Go to chapter 1 or from yesterday. Go to chapter 1 and for this section, this section is a W10 by 49. So what is the width of the flange? Go to chapter 1, 1049. Chapter 1 for W10 by 49, what is the width? BF. How many inches? 10? Okay. So, if this is 10, right? And look at this in here. This is 1.5, and I need this dimension from here to here. This dimension. I need this dimension. Estela, look. This in here is 10. Yeah, good. Stop. You got it. So it's going to be 10 minus 5 is 5. 10 minus 5 divided by 2. So this distance, like everybody got it, 2.5. All right? All right. So, and for the the flange is going to be from the length, is going to be from here all the way to the end. So this is going to be the for the double L. This is the width and this is the width. The length go from this ball all the way. So what is this distance from here to the end of the flange? From here to the end of the flange, what is this distance? Exactly. So it's 5 plus 1.125, 6.125. So this is what I have in here. The 2.5 that you gave me, 6.125, is a double L. So just to show you, like yesterday, this is a double L. So the gross area in shear, is 1, 2. Why do I have a 4 in there? Yes, Adrian. We always measure from the center of the hole. Remember, from the center of the hole. So, look, the bottom line. So I had 2 of this on the top and 2 on the bottom, so 4. So the gross area in shear is 4 times this distance. What is this 0.56 that you told me before? The thickness of what? What is this? Thickness of flange. So I have 13.70. The net area in shear, I'm saying the gross area 13.7 minus 4 lines, 2 at the top, 2 at the bottom. Look, 1 hole, 2 holes, 50% of the hole is clear in here. 1 hole, 2 holes, 50% of the hole. So I have 4 lines, 2.5, 7/8 plus 1/8. We always consider the 1/8. The only time that we consider 1/16 is when we are doing bevel. Times the thickness, because an area, thickness of the flange, 8.12. The net area in tension, we had 1, 2, and 2 at the bottom, 4. This dimension is 2.5. From here to the end, 2.5. And so 2.5 minus, I had to subtract half a hole. 7/8 plus 1/8. So times 56, 8.2. So I'm doing it here. This is the formula that we use for block shear, 0.6 FU net area in shear plus FU times the net area in tension is more equal to 0.6 FY gross area in shear plus FU net area in tension. So 450.91, 450.96. Now I need to compute the web. And when we look at the web is going to be AU. Can you repeat whiteboard? Yes. we had 2.5 top flange. There are twice, two of this, and there are two more at the bottom flange. So 4 times this dimension, 4 times this dimension minus half a hole. That's the 4 count. Adrian, do you get it? You very well. So look, so what happened here? 450.91 for the flanges. I need to do the web. So for the web is going to have a shape that is a U. Here, here, and from here. So I want you to look at this. This is the same dimension that we had before, 2.5, 2.5, and this is 1 and 1/8, so 6.125. This dimension here is given as 5. So go ahead and compute the block shear for the web. Go ahead and compute and bring it to me on Monday because we run out of time. I know that you have to drive to go to the next class and you're running late, so you're only doing one flange and done. Yes, you can always do one flange, and it's like 6 plus 6 is 12, right? Or 4 and 4 and 4 is 12. It's the same. As long as you consider all of them, this is exactly the same. So, like I was saying, we're running out of time. We're going to continue on Monday. If you need me during the weekend or today or tomorrow, I'm available. Don't forget to compute, do the block shear for the web for me. I know you have another class. Any questions or anything? You talk now. Yes. Any other question? Okay. Well, I see you Monday or see you later, whenever you need. That's all for today.